Hey, what's up, Logic fans? Welcome to our first section of Chapter 3. So we're starting propositional syntax today. I'm going to talk a little bit about what that is, but this is our first section in Chapter 3, 3.1, and we are going to go over rules of inference for and or ampersand and wedge. Okay, and I'll explain all of that. Let's rock. Okay, so let's take stock of the course for a second, and I'm going to introduce the notion of syntax. So um, think of the first three chapters of the course, chapters 1, 2, and 3, as a sort of unit, okay? In chapter 1, we developed a sort of symbolic apparatus, how to symbolize in symbolic logic. So you got your capital A, wedge, negation B, or something like that, okay? And you learned how to put all that together with parentheses and everything. Then what we did in the previous chapter, chapter 2, was we turned around and we gave, I didn't really tell you this is what we were doing, but we gave a semantic analysis of that symbolic apparatus developed in chapter 1. So, for example, okay, let's take a look here. So, you had a sentence like this, okay, and let's just take a look at this one as an example. You learned how to symbolize it, and then you thought about it in terms of truth values. All right, that was all semantics, okay? So you learn to think about it like, well, it could be a situation where both A and B are true. It could be a situation where where A is true and B is false, right? And sort of you learned all possible assignments to it, and you could see that this was a contingent sentence, and you were assigning truth values, and you were letting those truth values sort of give meaning to the statement for you, okay? And then we analyzed validity in terms of the truth tables too. From these propositions, does this other proposition follow? Does the truth of these propositions guarantee the truth of this other proposition, right? And so because we were thinking about it in terms of meaning and in truth and falsity, that was all semantics, okay? Now what we're doing is we're pulling the rug out from under you, and we're saying, okay, check this out. You can look at validity from two different but equivalent perspectives. We're not going to prove that they're equivalent. That's beyond the scope of our course. But I do encourage you to talk about those proofs with your professor. They're called soundness and completeness proofs. But what we're going to do is we're going to say, okay, stop looking at this in terms of what it means, in terms of whether it's true or false, and start thinking about it just as a random collection of symbols. So this is literally now going to be read, it's not going to be read, either A is true or B is true. Instead, we're going to read it AVB. And it just has no meaning. It's a random collection of symbols. Now, the symbols are put together in the same way specified in 1.7 and 1.8. So how they're combined together is all the same, okay? But we're no longer thinking about it semantically in terms of meaning. We're thinking about it syntactically. It's a random, meaningless string of symbols, and what I'm going to do is I'm going to give you different rules for how you can manipulate these symbols. In other words, we're going to be looking at validity syntactically. All right, so there's a bunch of rules you can follow that will allow you to derive certain strings of symbols from other strings of symbols, and that random arbitrary process of how to manipulate these meaningless strings is another way from sort of viewpoint from which you can view validity. Okay, so there's the semantic point of view and there's the syntactic point of view. Some of you are going to like the syntactic point of view better. Some of you are going to like the semantic point of view better. They are equivalent, okay? Like I said, we're not going to prove that, but okay, that's the big picture idea. Let's jump into this, and so you can sort of see what's going on with syntax and rule following. Okay, so let's just jump straight into this because I think it's the best way to get the idea. So what I'm going to be doing is I'm going to be giving you some rules that allow you to infer one string of symbols from another string of symbols. For example, our first rule of inference, I had to switch this, sorry about that, we're doing rules of inference. Our first rule of inference is known as simplification, or sometimes just Simp for short. And what it says is if you have a random, arbitrary, meaningless string of symbols that looks like this, okay, you can write down this string of symbols, not making any other changes to it, and you're allowed to do that by the rule Simp on line 1. That refers to this one right here. I use simp on line 1, and I'll explain this part shortly, okay? But the basic idea is given a string of symbols like this, you're allowed to write down a string of symbols that looks exactly like that, making no other changes, okay? So let's see how this works in practice. So in this case, what we're going to do is we're going to do a little bit of a practice problem that you've never seen before. I'm just going to walk you through it because you've never seen it before. So what we're asked to do is we're supposed to show that this argument here is syntactically valid, but we're not thinking about it as meaningless. Basically what you're supposed to do, syntactically valid, is show that you can get from this string, which is given as a premise. Okay, here's a meaningless string of symbols. Can you get from it, using our rules, you only have the one right now, simp, to this string? And of course you can, but your job is to show it. So let me illustrate to you how it would be shown that you can do this. Okay, so here's what the demonstration of syntactic validity would look like, okay? Basically what we have here is we have a grid, and you've got 2 columns, okay? And in this, it's just indicating what line you're on, all right? And over here, you're giving your rationale for how you got from one line to the other. So typically what we do is we collect all the premises in the upper couple of lines, and then sometimes I just put a space between the premises and the non-premises. But in this case, we only have the one premise, so the space doesn't mean anything. You can take it out if it bothers you. But what I'm doing is I'm saying I have this string of symbols, and that was given as a premise, okay? And I can get from this string of symbols to this string of symbols by application of the rule simp on line 1. So this 1 here refers to this line. I use simp on this line, on this string of symbols, where the value of p was just a. And that makes sense because simp says, okay, if you've got a p and an ampersand and a q type thing, then you can write down the p part, okay? And so that's how this is going to be demonstrated. And don't forget to put your QED, okay? So this sort of little box here shows that it's possible to syntactically deduce this conclusion here from this given. It's possible to syntactically deduce this string of symbols from this string of symbols following our rules. Let's try another example of simp. So here we've got a given string of symbols. Looks just like this. And from this given string of symbols, you're supposed to get a string of symbols that looks like this. And you can only move from this one using our rules. And you only have the one rule right now to worry about, which is simplification. So you're going to use simp to do it. So pause now and see if you can produce a syntactic deduction of this string of symbols from this string of symbols. We'll come back and I'll show you how it's done again, just so that you know, as you're getting more and more familiar with this. Pause now. Okay, so I'm going to give you a bit of a hint here, and so I've sort of partially filled in the syntactic deduction here, and you've got your premise, A and B, excuse me, and C, and you're supposed to go from this string to this string, and then from this string to this string using the rule simp. So see if you can fill in what has to go here to complete this. Pause now. Okay, so it's only the one rule right now, so it's not too bad, right? But you use simp on line 1, and notice simp on line 1 did get you this whole thing, so you could actually think of it in parentheses if you wanted, but following our sort of stylistic conventions, I've omitted them. But yeah, you've done that. Okay, so you've used simp on line 1, but what was p equal to here? Well, in this particular case, p was equal to a and b. Okay, and in here it might help to see the parentheses. All right, so you could think of it that way. Now, what about this one? Well, this was simp, right? We got this string of symbols from this string of symbols using simp on line 2, of course. So it was from this one that we got it, and in this particular case, p was just equal to a. Okay, so this is a syntactic deduction of this string of symbols from this string of symbols, okay? And every line contains either a premise or an application of a rule, and never more than one, okay, per line. And it's done correctly. Now, I want to show you a couple of items here, okay? So some students want to know, hey, Ash, could I have gone from, let's just say I had gone from 1 immediately to this. Could I have done that? And the answer is no. You could not have done that. This is not allowed. This is strictly prohibited, okay? Simp does not allow you to do this. You have to follow the form, okay? So the way to read this rule is that given P and Q where, you know, this and here is a main connective, you can infer the left conjunct, okay? There's no left conjunct that just has A all by itself, and so this is not allowed, okay? Nor could you have inferred, you know, B by itself. That wouldn't have allowed. And no, you could not have inferred C. Now, intuitively, B does follow from this. Okay, so if you're looking at this semantically, you're thinking, well, if this thing is true, then certainly B is true and C is true, so it should be possible to get B and C. It is possible, just not from the rule simp. We're going to have other rules that allow that. And this is syntax, so the rule following really matters. That's the whole point. You've got this arbitrary string of symbols, and you've got these rules for how to manipulate them, okay? So often I like to tell students, all right, you know, I'm God, and I'm making up these rules, and you will follow my rules, and if you don't follow my rules exactly, then I'm going to be a vengeful and wrathful God, and I'm going to punish your grade. Okay? No, I'm just kidding. I'm not going to punish your grade. But that's the point of syntax. It's not semantics. Okay? And you have to follow. It's all about rule following, and so we do want to be a little bit persnickety about following the rules precisely. So on that note, let's go through a couple of examples just to go ahead and make sure that you're following what simp allows and what it doesn't. Is this a legitimate use of simp? Is it or is it not? And if so, what's the value of P here if it is a legitimate use? If it's illegitimate, then don't worry about it. Pause now. Okay, so from this, you can indeed infer this. So this is legitimate. This is okay, all right? There's nothing wrong with this, all right? And in this case, the value of P was just A. Let's try another one here. So legitimate or illegitimate, and if it's legitimate, what's the value of P? Pause now. Okay, this is also legitimate. This is okay. Go ahead and do it, right? But you have to be a little bit careful because the value of P is now A. So this is why we did all the substitution instance stuff from chapter 1. So if you need to review that in 1.7 and 1.8, go back and check it out, okay? But yeah, this whole left part here is just P, and this is the main connective, and simplification does allow you to make this move. That's perfectly okay, all right? So go ahead and do it to your heart's content. Let's try a couple others. So try this one. I took the not off here, left everything else the same. Is this legitimate or illegitimate? And if it's legit, what's the value of P? Pause now. Okay, this is illegitimate. Don't do it. This is criminal, right? Prohibited. Do not do it. Simp does not allow this type of thing. You're allowed to infer P, making no other changes to P. Okay, so that's the key feature there. You can only write down P. It's like you're copying and pasting P down, okay? And so that's not allowed. What about a case like this? Is this legitimate or illegitimate use of simp? And if it's legitimate, what's the value of P? Pause now. Okay, this is illegitimate. The main connective here is negation. And this says you have to have a string like this, whose main connective is ampersand. Then you can write down the left part. So illegitimate, criminal, prohibited, do not do it. Okay? This is bad. All right? Simp does not allow this. Okay, let's spill on to the next video. We'll keep doing these exercises so that you feel like you really understand what simp allows and what it doesn't. So look for video 3.1b. Catch you there.